So on Friday, I hinted at being able to follow these steps in order to use your calculator. So they're very easy. You hit math, you hit 9, and what's going to pop up on your screen is an integral that looks like this. So it's going to be the integral symbol. It's going to have a box here, the box for the function, a D, and another box. You are literally going to just type in the 1, the 3, the x squared minus 2x plus 2, and then after the D, and X. So this acts as an excellent resource to check your math. The only way you can check it is if there is a bound. So we're going to talk about integrals without bounds. So this is a bounded integral, and it works best for easily infinite functions. I'm not worried about the other ones. If you want to write down your answers, you can. So in this case, you had 3 plus 2. You would type it in exactly as you see it on that screen. On that screen, you would hit the number 3, the plus sign, enter your integral exactly as it is, and hit enter. Another thing you gotta be careful is that if you are doing trig and your bounds are in radians, your calculators. If it asks you to find the bounds of a trig function where a tangent, secant, or cosecant have asymptotes, you will have to break the integral up to where the asymptotes are. So I wrote 5/3 originally. I think the number here was pi halves, and then that did not work because it was on the infinite integration. Okay, so same idea. This is if you do it from the graphing screen. So if you do it from the graphing screen, which we talked about the other day with the Riemann sums, it puts the area under that curve from the x-axis to the curve. And those are the steps to do it from the graphing screen. Enter your function in y1, hit second trace, go to 7, and then you just enter your 2 bounds. So again, something we significantly hit on Friday is that all continuous functions are integratable. All continuous functions are integratable regardless of if they have a cusp or a corner, because that cusp or corner does not affect finding the area under the curve. If the curve itself is on the x-axis, then your area is 0, but it is still a value. So the definition of an integratable function is as follows. You can find the area under the curve for the integral from a to b of f of x dx. That area is equal to the area above the x-axis minus the areas below, or from one piece to another. So in the case of this example here, we have the integral being evaluated from a to b. But at point C, the curve shows from above to below. So areas above are considered to be positive integrals. Areas below are considered to be negative integrals. So what we would do is add the area integration for the above, which is 3. Subtract from it the area below, which is 7, to get our total area of -4. So some of your delta maths are also going to have that, where it gives you the sums of the parts, or you have to find the areas of those parts because they are nice shapes. But what you need to know is if you are looking for the integral, it's the totals of the above minus the totals of the below. integrals can be negative. So again, you'll see the area is given to you as a positive 7, but the integral value would be a negative 7. So we would say the integral from C to B is negative 7. That gives me the area under the curve. Being A. From A to B is negative 4. The reason it's A and not 0 is because we don't know this area. So it was only from the dashed line to 0. So not 0. Integrating a function with discontinuity is again different than integrating a function with discontinuity for derivatives. So if you're integrating a function with discontinuity, you're simply going to break your integral into both parts. So we have a piecewise function that takes on negative 2 to 7 where x value is less than or equal to 3. So I would take 3, plug it in, negative 2 times 3 is negative 6. Negative 6 plus 7 is 1. So at 3, we have our point 1. And then that slope is negative 2. So again, you're going backwards and down. So that is my curve from 0 to 3. So again, it asks me to evaluate the integral from 0 to 5. So what I'm going to do is evaluate the integral from 0 to 3 of negative 2x plus 7 dx. And I'm going to add to that the integral from 3 to 5 of 4 dx. So when we're doing this, we are looking at those areas under the curves in order to find these values. So we would say that the area under the curve for the second integral is going to be from 3 to 5. So that's a rectangle with a height of 4. So that area is going to be 4 times the length of the width, which is b minus a, so 2. So we're going to add 4 and 2. And then we're also going to find the area under the curve from 0 to 3. That area is going to be a trapezoid. So we're going to take 1/2 the height, which is the b minus a again, in this case 3, times the height of the width. So the tallest width is at 7, and my other width is 1. So we're going to take that, we're going to add the area of the trapezoid to the area of the rectangle to get the area under the curve. So 8 divided by 2 is 4. 3 times 4 is 12. So the area of the trapezoid is 12. The area of the rectangle is 8. So the value of the integral from 0 to 5 is 20. So again, if you have two curves or a piecewise curve, you take into account where they jump or have breaking points to find the areas under each we're again using area and you have a change from positive to negative, we also have to break that up. So this graph goes from -1 to +3. It has a initial starting height on the y-axis at -1. My slope is a positive 1/2, so tells me it's going up 1 and over 2. Which tells me at 2, I am going to need to create my new integral, because the area from -1 to 2 is going to be negative, and the area from 2 to 3 is going to be positive. So this time, the integral from -1 to 2 is going to be a trapezoid. This time, the height of the trapezoid is actually the height or the value of the function at -1. So this height right here is -1 plugged in, so you get -3/2. And then base 1 is going to be the distance from here to there, which is 1. Base 2 is going to be the total distance, which is 3. So we have equals 1/2 height times base 1 plus base 2. And again, this entire answer is negative. I'm just going to tack that negative on. You could also have seen that that negative would have occurred right here with my height at -3/2. So again, it was a -3/2 height, so that negative could also be placed with that as well. Then you're going to find the area from 2 to 3. So this area will become a triangle. Straight across to my point. I said, okay, I'm going to do a straight line. What I have to do is get rid of my +1. Because the height is still -3/2. My base is still 3. I just don't have that extra height. And then we're going to add to it my little red triangle. So I have a base of 1 and a height of 1/2. Okay? So -3/2 times 1/2 times 3 gives you a -9/4. 1/2 times 1/2 is 1/4. So -9/4 plus 1/4 gives you -8/4 for a value of -2. Now, your calculator could have found that integral as 1 piece. We have to currently find it as 2 because we're using shapes and not our power rule. Alright, so evaluate the integral using the integrand and areas. So again, we have this curved shape. We have 1/x plus 3. So we are going to find that area under that curve. So that is the distance, essentially, from -3 to 3 and the x-axis. What happens is you can think of this as two shapes. You could do a rectangle and a triangle, or a trapezoid. This one actually is. All areas are positive, so we don't have to worry about subtracting anything from something else. So sketching quickly is helpful to see the shape. Sketching quickly is helpful to see the shape. So I believe in your textbooks, problems in the middle there are evaluate the area under the curve using shape. So that is like this example here. Okay. Evaluate the integral using the graph of the integrand. So this one's a little more complicated. What I see in here is a square root function. Anytime I see a square root and I'm doing an integral, I'm thinking a circle. So this is going to be a circle shifted down. Its radius is 2, so it's really nice that my bounds are from -2 to 2. Its radius is from 2, so the bounds being from -2 to 2 makes this very nice. So think about a normal circle whose radius is 2. That means it usually goes up from 0 to 2, and it's usually at -2 and 2. So I'm just going to imagine all of those points shifted down 3 units. So instead of being at a +2, it's going to be at 1, 2, 3. Instead of being at -2, 0, it's going to go down 1, 2, 3. So what happens then is that if we're evaluating the integral, we are not finding the area necessarily of the circle. I want to find the area between the circle and the x-axis. So this goes back to like the days in geometry when you had like a rectangular shape or a square, and you had like the circle inside the square, and you wanted to find the areas of like the shaded borders around that, and you had to find the area of the square, and then you subtracted the area of the circle, and that gave you like the leftover corner pieces. So what we're going to do is something similar. We're going to find the area of the big rectangle outlined in blue. So we're going to say it's equal to the area of the rectangle, so that's 1, 2, 3, 4, times down 1, 2, 3. So the area of the rectangle is 12. And then that blue rectangle would be everything in here. So if I want to find the pink, what do I have to subtract away? Exactly. So we're going to subtract away the area of the semicircle. we get that the area of that pink region is 12 minus 2 pi, but all of that is below the curve. So really, it's all additionally negative. The area below that is negative 12 plus 2 pi. So that everything is below. The next one is the one that I think is like the most new, because this is the one that your bounds are letters and not numbers. So since my bounds are letters, they're just generic points on the x and y axis. They can be as close together as you want, or as far apart as you want. Typically, I believe the textbook is going to say that b is always greater than a. So we're assuming that b is always the further away point, because if b is not, then it like kind of gets messy. So 3 theta, or 3 whatever, any variable, just represents an x. So 3 theta does not change the rules. It's no different than if this was 3x. So if it was 3x, then you would just draw in your curve as if it went through 0, 0, up 3, over 1, up 3, over 1, so on and so forth. So that would make those points A, f of A, B, f of B, but the f of A or f of B is really just plugging into f of 3 theta. So f of A is really like A, 3A. And f of B is really like B, 3B. And you can see from that picture and those points that the area of that curve is a trapezoid. So base 1 is 3A, base 2 is 3B, and then the height is that distance from A to B. So again, the height or the distance is always B minus A. So in this case, we just don't know B, A, etc. That is your integral value. Because then once you knew A and B, so if like in the future you were told A is 4 and B is 9, you would just go back in and plug in 9 minus 4, 3 times 4 plus 3 times 9, and work out your answer. So you're finding it in general to use it in the future with a number. And the last part is just never forgetting that you can only integrate continuity. If you are asked to integrate an area including discontinuity, it's not differentiable. So like if I asked you to integrate from 0 to 1, 0 is undefined, it is not in my domain, it is discontinuous at 0. The limit does not exist. Remember, integrals are simply just summation limits.
Will following students please report to the office? Aubrey Bevan, Aaron Bevan, Wayne Weaver, Nathan Patterson, Stephen Bing, Nick Gato, Sierra Bamberger, Reagan Watkins, Brett Horner, Emiliano Perez Salinas, Molly Sheets, Joseph Horner, and Michael West.